Welcome to RoRe Academy YouTube channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. Here, we break down the art of designing, assembling, and testing real engineering systems, helping you understand the science and creativity behind innovation in power electronic-centric systems and devices in our 5-minute video clips. If you're into EVs or work with electric cars, you need to check this out. The AutoMaxi Ultra EV Diagnostic Scanner is seriously one of the best tools out there for deep-dive battery diagnostics and full system testing on electric and hybrid vehicles. It's fast, accurate, and super easy to use. Honestly, a total game-changer if you're serious about understanding your EV inside and out. So if you want to grab yours, just click the link in the video description below and check it out. In Part 2 of our BYD Seal Power Domain Controller Teardown series, we shift our focus to the traction inverter, the core power electronic subsystem responsible for converting DC energy from the battery into three-phase AC power for the electric drive motors. In this video, we take a close look at the inverter structure, examining how BYD has implemented a high-power, silicon carbide-based inverter within its integrated power domain controller. We'll analyze the power module layout, DC link architecture, current sensing strategy, and gate drive and control interfaces that enable high efficiency, fast switching, and precise torque control. From semiconductor selection and thermal design to packaging and electromagnetic performance, this teardown provides insight into the engineering trade-offs behind a modern, production-ready EV inverter. This analysis is intended for EV engineers, power electronics designers, researchers, and students who want to understand how real-world electric vehicle inverters are designed, integrated, and optimized. Let's begin Part 2 of the BYD Seal Power Domain Controller Teardown with a deep dive into the inverter architecture. In Part 1 of this series, we disassembled the power domain controller to identify its key internal hardware. This included the output current sensor module, DC link capacitor module, a high-power fuse, 2 high-voltage power relays, a silicon carbide power module, and a dedicated DC current sensor. Each of these components plays a critical role in handling high voltage, high current, and fast switching transitions, ensuring efficient energy conversion, accurate current measurement, and robust system protection across all operating conditions. In this part of the series, we turn our attention to the core elements of the BYD Seal traction inverter. We begin with a detailed discussion of the inverter control board, examining how BYD implements real-time control, sensing, and protection to achieve precise motor torque control and high system efficiency. We then take a close look at the silicon carbide power module used in the inverter, analyzing why SiC devices are selected for this application, how they enable higher switching frequencies, lower losses, and increased power density, and how they are integrated from both an electrical and thermal perspective. Finally, we examine the DC link capacitor module, discussing its role in voltage stabilization, ripple current handling, and transient performance, as well as the design trade-offs involved in selecting capacitors for high-power automotive inverters. Together, these elements form the foundation of the BYD Seal's inverter architecture, and understanding how they interact provides valuable insight into the engineering decisions behind a modern, production-ready electric vehicle powertrain. The BYD Silicon Carbide Power Module, BM840F12B34U2, is designed to deliver low switching losses, enabled by BYD's advanced SiC MOSFET chip technology. This makes the module well-suited for high-performance traction inverter applications, operating efficiently across a switching frequency range of approximately 1 to 30 kHz. In this section, we also examine the internal device structure. You can see the die cross-section SEM images, along with the optical views of the die layout and the die cross-section in optical microscopy. These images provide insight into the device architecture, layer structure, and packaging approach that contribute to the module's electrical and thermal performance. The BYD Silicon Carbide Power Module, BM840F12B34U2, is rated for a drain source voltage of 1200 volts and a nominal drain current of 500 amperes, making it suitable for high-power electric vehicle traction inverter applications. The module operates with a gate source voltage range of -5 volts to +18 volts, enabling robust gate control, fast switching performance, and reliable operation under demanding high voltage and high current conditions. Here, we can see the package outline of the BYD silicon carbide power module, BM840F12B34U2. The layout clearly highlights the three-phase inverter structure, with the positive and negative DC terminals, P and N, prominently identified. This module integrates a complete three-phase power stage, specifically designed for electric vehicle traction inverters, enabling compact packaging, low parasitic inductance, and high-efficiency power conversion under high voltage and high current operation. Shown here is the traction inverter section of the BYD Seal power domain controller, alongside its equivalent circuit diagram. The inverter is implemented as a three-phase, two-level voltage source inverter, which converts the high-voltage DC from the traction battery into a controlled three-phase AC supply for the electric motor. At the heart of the traction inverter is the DC link capacitor module, a critical component responsible for stabilizing the DC bus voltage, absorbing high-frequency ripple currents, and minimizing voltage overshoot during fast switching transitions. This ensures stable inverter operation under high load and high switching frequency conditions. Power conversion is handled by the BYD silicon carbide power module, BM840F12B34U2, which integrates the three-phase switching stage using advanced SiC MOSFET technology. Mounted directly on top of the power module is the inverter control PCB, providing gate driving, protection, and real-time control while minimizing parasitic inductance and improving switching performance. Finally, the output of the three-phase traction inverter is monitored using a dedicated output current sensor, enabling precise current measurement for torque control, efficiency optimization, and functional safety. Together, these elements form a highly integrated, high-performance traction inverter optimized for modern electric vehicle applications. Thank you so much for watching today's video and exploring how the traction inverter of the BYD Seal is put together, while highlighting its critical hardware components. Remember, here at RoRe Academy YouTube channel 2.0 you watch, learn, and understand how to prototype. See you in the next video for part 3. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.